Warm up, warm up. Negative 3x squared minus 2x minus 1 is f of x. Set up and simplify f of x plus a minus f of x over a for some a greater than 0. Remember, this is not only my favorite problem. The reason it's my favorite problem, this is the average rate of change. This is the average rate of change between the, bless you, between the points x, f of x, and x plus a, f of x plus a. So we did this when we did the falling textbook, if you remember. So you should be able to set up that ratio, that ratio by yourself without me even giving it to you. But if this were a test question, I would give it to you. So let's go ahead and set it up. The first thing I'm going to do is I'm going to realize that I need f of x plus a. My function is negative 3 input squared minus 2 input minus 1. And then I'm going to have minus f of x itself, which is minus 3x squared minus 2x minus 1 all over a. So you can see I have the two forms there. Negative 3 blob squared minus 2 blob minus 1 minus negative 3 blob squared minus 2 blob minus 1. It just so happens in the second blob, I have an x, right? But here's the key. What am I going to plug into the two parentheses where there used to be an x into the first function? X plus a. X plus a goes in there. You plug it in twice because there's two x's. That's important. People don't do that. They make mistakes. X plus a, x plus a. That's going to get you points on the test right there. Now we just have to expand it out. Now, how do we expand a binomial squared? Remember the little ditty? Square multiply double, square. Square multiply double, square. Now, we're going to do two things at once. We're going to square multiply double squared, and we're going to distribute the negative 3 as we go. Why can we do that? Because we are honors. We're awesome. So here we go. If you square the first, you get x squared times the negative 3 gives you negative 3x squared. When you multiply and double, you get xa times 2, which is 2xa. 2xa times negative 3 is negative 6xa, or ax. Well, I'll do it as ax. Doesn't matter. And then you square the last, you get a squared, and you distribute the negative 3, you get minus 3a squared. So we did two things in one there, right? Square multiply double squared, and distributed the negative 3. Now we distribute the negative 2, and we get negative 2x minus 2a minus 1. That takes care of the first expansion. Now we go to the second one. We distribute the negative, and we get plus 3x squared plus 2x plus 1. And all of that is over a. Don't forget it's all over a. Now here's your checkpoint. If you do it correctly, anything in the numerator without an a in this case should cancel. Make sure it does. Negative 3x squared, positive 3x squared. Negative 1, positive 1. Negative 2x, positive 2x. And what's left? I'll highlight it. We get negative 6ax minus 3a squared minus 2a. They all have an a in there, don't they? So the next step is to factor out that a, and we're left with negative 6x minus 3a minus 2 all over a. And then the fun step, right? This is the most fulfilling step for me. Those divide out, and we're left with negative 6x minus 3a minus 2. And there's your answer.
Did you not also factor out a negative?
You could factor out a negative, yeah. Yeah, we could factor out a negative. If you want, you could call it 6x plus 3a plus 2. Yeah. I'm going to be looking to make sure you factor out the variable. If you want to, if there happens to be another common factor in there, like a negative 1 or a 2 or something, feel free to factor it out as well. But the important thing to factor out is whatever that variable in the denominator is, because it's going to divide out. Okay? So any one of those final answers is good. Good. Sick and bears, kind of. All right. Any questions on that? My favorite problem. Okay. Let's get back to the notes. We love our notes. Give us more notes. We already did our long division on this problem. 4t minus 3 over 2t minus 5. And when we got our answer, we rewrote it as the quotient, negative 4/5, plus the remainder over the original divisor. Okay? So if you want to write that out, it's going to be the quotient plus the remainder over the original divisor. Now, why does that work? I just want to show you. If I had a ratio like 23/5, that would be 23 divided by 5. Oops, divided by 5. 5 is the divisor. It goes in 4 times. You subtract and you get a remainder of 3. This is your remainder. So you could write 23/5 then as 4, the quotient, plus 3 left out of the original 5. Okay? That's all we're doing. We're just doing it with polynomials. Okay? All right, now that I get it into this format here, I can put it in standard transformation form. So that negative 4/5 is going to go at the back. The negative 7/5 goes in the front. And what I'm left with then is 1 over negative 5t plus 2. Is that standard transformation form? Mm. Very good. It is close, but it's not quite there. I got a coefficient of negative 5 in front of the t. If you leave it in this form, you're going to think it's shifted left 2 units, but it's not shifted left 2 units. I got to keep going. So, oops, highlighter time. Already early in the week. Negative 7/5 all over 1, or 1 over negative 5, parentheses t, and then minus 4/5. Now the question is, what do I get when I factor a negative 5 out of a 2? What's 2 divided by negative 5? 2 over 5, negative 2 over 5, yeah. Remember, it's what you started with divided by what you're factoring out. There is the standard transformation form. I'm not going to write it down, but let's just talk about what we're doing from left to right, okay? The negative in front is going to be an x-axis reflection, right? The 7/5 is going to be a vertical stretch, because 7/5 is bigger than 1 by a factor of 7 over 5. Yeah, good, 1.4 times bigger. The negative in front of 5 is going to reflect it across the y-axis, and then the 5 is going to be a horizontal compression by a factor of 5. That takes care of the final shape. So we're doing a double flip, right? Flip, flip. And then we move it right 2/5. That'll move the vertical asymptote to 2/5. And then we move it down 4/5. That moves the vertical asymptote down to 4/5. You want to sit on the other side so you don't have to keep turning around? You can just put the chair over here. Okay. Now let's think about the parent function. What happens when I do a double flip? It starts living here and it starts living here. If I flip it across the x-axis, it goes from green to purple. Yes, yes? Okay, so let me get rid of that original graph. Now I take the purple graph and I reflect it across the y-axis, and it looks like this and like that, and now we get rid of the purple. It looks like exactly what we started with, right? So flipping it twice was kind of like not even flipping it at all, wasn't it? Well, notice how algebraically we can do that. I can actually multiply this negative times this negative. And what's a negative times a negative? A positive. So it could be equivalently equal to the positive value with no flips, okay? So it just so happens it has the exact same shape. So as complicated as this one was, the graph is actually pretty easy. We just come over here to 2/5. We draw a vertical asymptote. We come down here to negative 4/5. I'll just come down here a little bit lower. Negative 4/5. We draw a horizontal asymptote. And then it lives in this quadrant here. And it lives in this quadrant here. Does it have a y-intercept? It sure does. Let's go ahead and find the y-intercept. For the y-intercept, I'm going to plug it back into the very top, into the original. It's going to be negative 3 all over 2. Remember, for the y-intercept, you can plug it into any version of our function. We have the original version in black, and then we have the blue, the purple, the red, and the green. I'm going to plug it into the original version for the y-intercept, just because everything that has a t in it goes away. Okay, and then once you have the graph, you can talk about all the characteristics. So now you can do that one that was in your homework like that. You just have to do long division first. And then it turns into a typical fun problem. All right, comments or questions on that? Oh, let's do one question before we walk away. What would be the limit as x goes to, wait, is this x of t? Yeah, so it's t. The limit as t goes to negative infinity of x of t. Negative 4/5. Okay, good. I can't trick y'all at all. I don't even want to trick y'all. I just want to quiz y'all. Yeah, we're approaching the horizontal asymptote, which is at negative 4/5. Very good. Very good. Oh, I got to do one more just because it's irresistible. What would be the limit as t approaches 2/5 from the left-hand side of x of t? Negative infinity. Good. Can't trick y'all. Good. It's going down. As we approach from the left, it's going down, 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 down towards negative infinity. You get the idea, right? All right. What would be the general limit at negative 3/2? What would be the general limit as x goes to 0? Sorry, on x of t. Sorry, I gave it away. Negative 3/2. My bad. Yeah, my bad. Because it's continuous there, the limit is the same as the function value. Okay. Fun stuff once you have the graph. But it started with long division, didn't it? Long division. Okay, example 6. There's several different ways you can get the same graph algebraically, like what I mentioned here. I could actually multiply these two together and end up with a positive value, and it would be like, instead of flipping it twice, it would be like flipping it not at all. There are several different ways you can get the exact same graph through equivalent transformations, and that's what example 6 is. So on example 6, we're going to start with the parent function 9x, or f of x, and we're going to do this transformation to it. We're going to replace x with negative 9x. For any function, what would this do to the graph of f of x? If you replace x with 9x, what does this do every time? It's horizontally or vertically? It's a horizontal what? Compression by a factor of what? 9. It's going to take every graph and horizontally compress it by a factor of 9. But there might be another way to get the same graph depending on what our parent function is. So if I do this one right here, f of x equals x, g of x is going to equal, I'll replace x with the parentheses. I'll replace x with the parentheses, and I'll drop a 9x in there. Okay, so the first one is always going to be a horizontal compression by a factor of 9. That one's going to be the first one every time. In fact, I'm going to copy that so that I can paste it. But algebraically now I can manipulate this. I can actually bring the 9 outside of the parentheses without any problem, right? I could bring the 9 outside the parentheses without any problem. And that would make it a what? Now it's on the outside. Instead, it's an A value instead of a B value. Vertical stretch by a factor of 9. Yeah. So if we have the original line, which looked like this, we'll call this y equals x. If I horizontally compress it by a factor of 9 or vertically stretch it by a factor of 9, I get 9x. So I can either obtain the graph by vertically stretching it, or I can horizontally compress it by the same amount, right? By a factor of 9. And that's just unique to the line. The line is kind of boring in that respect. What does it mean to be inside the linear function? Well, you just have to add parentheses, right? What does it mean to be outside the linear function? Don't really need it, okay? It's the linear function. Now, x squared is a little bit different. Let's go ahead and create g of x. I'm going to replace x with parentheses, and in place of x, I'm going to put 9x. So what would be the very first transformation that would do the graph of x squared? Horizontal compression by a factor of 9. Let's go ahead and sketch it first this time, because this one's a little bit different. The graph of x squared looks like this. This is x squared. And if I horizontally compress it by a factor of 9, that's going to bring it in like this, right? Horizontally compress it. So it's going to make the graph effectively what? Steeper, yeah? Horizontally compress it. Get your hands on each side, push it towards each other. It's going to make it steeper. Is there another way to obtain that graph? Well, I claim yes. Instead of compressing it horizontally, I could take the gray graph and pull it up vertically like this. That would be equivalent to some kind of vertical stretch, right? There would be some kind of vertical stretch by a factor of what? 9? Is it the same? No, it's not the same. In fact, let's see why it's not the same. If I come back up here and I look at 9x quantity squared, I can't just bring the 9 outside the function like I did for the linear function. But what can I do? What is 9x times 9x? This is the same as 9 squared times x squared, which is what? 81x squared. Oh, so it's equivalent to a vertical stretch by a factor of what? 81. Yeah. See? Each function has its own algebra attached to it. So for the line, you can just bring it outside because there's really nothing to do. But for the squared function, to get it from the inside to the outside, we have to what it? We got to square it. So a horizontal compression by a factor of 9 is equivalent to a vertical stretch by a factor of 81. These make great multiple choice questions on a test. Okay, let's look at letter C. The first one, we'll create it. Well, let's just create the function first. G of x is going to be parentheses 9x quantity cubed. And of course, what's the first transformation that does? Because it's a 9 on the inside. Horizontal compression by a factor of 9. All right, let's see what that's going to do. Let's go ahead and sketch this puppy. X cubed looks like this. It comes in and goes horizontal. Then it goes out like that. It has origin symmetry. It's an odd function. If I horizontally compress it by a factor of 9, I'm bringing this value in. I'm bringing that value in. 0 stays the same. It has the effect of making the graph water. It has the effect of making the graph steeper. Yeah. Now, I claim that I can obtain that same graph not by horizontally compressing it by a factor of 9, but by vertically stretching it by some amount. I could do the same thing. 0 would stay the same way. So this is equivalent to some vertical stretch by a factor of blank. Well, what do you think that factor is? Yeah, very good. You just do the algebra. You got to get this from the inside to the outside. You got to get 9 from the inside to the outside. Okay, and so this is the same as 9 cubed times x cubed. Well, what is 9 cubed? It's 81 times 9, which is 729 x cubed. Woo! So that's equivalent to a vertical stretch by a factor of? Man, that sounds like a lot of work, huh? So if you want to get the red graph from the green graph, you can either A, compress it horizontally by a factor of 9, which doesn't sound too bad, or vertically stretch that dude by a factor of 729. Don't thank you. That sounds like more work. But guess what? It's the same amount of work. You get the exact same graph. Y'all feeling it? You getting the idea what we're doing here? All right. Let's look at letter D. Let's create the function first. G of x is the square root of 9x on the inside. That's a b value. That's on the inside. So, of course, what's the first transformation? Horizontal compression by a factor of 9. All right, let's see what this puppy looks like. We got a lot of puppies in here today. I like dogs. The square root of x is in green. Oh, I drew it a little too steep. Let me draw it a little bit less steep. There we go. There's the square root of x. And I'm going to horizontally compress this by a factor of 9. So this comes over here. This comes over here. And it has the effect of making the graph water steeper, right? Well, I claim that I can also make this thing the same graph by vertically stretching it by some amount. I could vertically stretch it by some amount. The question is, what is that amount? Well, let me come down here and say a vertical stretch by a factor of question mark. We just do the math. If we have g of x equals the square root of 9x, how do I get the 9 from the inside to the outside? Square root. That's the same as the square root of 9 times the square root of x. And what's the square root of 9? 3. So I get 3 square root of x. So it ends up being a vertical compression, vertical what? Stretch by a factor of 3. Ain't no thing, nothing to it. Each function is unique. You just perform the math that the function says to do to get it from the inside to the outside. All right, let's look at x to the negative first, also known as what? 1 over x. Okay, let's look at g of x. G of x is going to be 1 over 9x. Remember, to be considered inside the reciprocal function means to be in the denominator. So, what does that mean? Well, let's see what the graph looks like. Here's the graph of 1 over x. And if I horizontally compress it by a factor of 9, I'm bringing this in, I'm bringing this in, and it looks something like this. It has the effect of making the graph water again. It makes the graph steeper. Yeah. Now, look at this. In order to get, and this is where you have to think, in order to get from the green graph now to the orange graph, am I going to stretch it vertically? I need to bring it down, don't I? I need to compress it by some amount. Yeah. I need to compress this thing. So this is going to be some kind of vertical compression by a factor of what? The question is by a factor of, how do we figure it out? Well, we do the math. 1 over 9x is the same as 1 over 9 times 1 over x. Yes, yes? Yes, yes. Is that all we have to do? There's our a value. It's a 1/9, so we know that it's less than 1, so we know it's going to be a compression. But it's by a factor of what? 9. We flip it. There you go. So notice that we knew before we even did the math. Before we even did the math, we knew it was going to be a compression, right? Because we graphed it. We graphed it. All right, we could keep doing this for all of these, and it's going to be kind of interesting. The absolute value of x, I'm going to skip. It's kind of boring. But let's look at the natural log of x. This one looks interesting. G of x equals the natural log of 9x. The absolute value of x works a lot like x. So of course this is going to be paced, a horizontal compression by a factor of 9. Now if we sketch this dude, the graph looks like this. It has a vertical asymptote right here, and there's the graph. If I horizontally compress it by a factor of 9, it's coming in, and it's coming in, and it's going to look like this. Now notice this graph doesn't go through 0, does it? This graph doesn't go through 0. So what would be the other way to get this green graph into the orange graph? Well, if you look above the x-axis, I'm going to have to stretch it, yes? I'm going to stretch it, but if I stretch the point that's on the x-axis vertically, what's 0 times any number? 0. That's not going to move that point over to this point, is it? There's no way to vertically stretch the x-axis, because that's where y is 0. I can't stretch 0 vertically because 0 times anything is 0. So what's another way to get that green point over to the orange point if I can't vertically stretch it? I can translate it. I can shift it, right? Now, if I shift it horizontally, it looks like it might work. But if I shift it horizontally, that's also changing the location of the vertical asymptote, isn't it? And do I want to change the location of the vertical asymptote? No. So what's the only option? If I can't compress it or stretch it, and I can't move it left or right, what's the only other option? Moving it up or down. Oh, look at there. If I just move my graph up a little bit, it kind of coincides with this one. You know, mine is just a sketch, but you can see that there might be some kind of vertical shift that's equivalent, right? Okay, let's see how we can figure that out mathematically. The second one, if I look at g of x equals the natural log of 9x, we have to remember a property of logs. Here's the property of logs, very important property of logs. The natural log of a times b is equal to the natural log of a plus the natural log of b. Okay, we're going to study that again later in the year, but right now I want to introduce that to you, and you should know that, okay? From here on out, you should know that. The natural log of a times b is the natural log of a plus the natural log of b. That's a beautiful property of logs. The log of a product is the sum of the logs. Logs make molehills out of mountains. They tear things down. So they change the operation from multiplication to addition. That works great, okay? So if we know that property now, we can expand this and we can say this is the natural log of 9 plus the natural log of x. And if I flip that around, I get the natural log of x plus the natural log of 9. And now here, and then a high point like this. Three full cycles, we can call them cycles if you want, or repeats. So I'm going to let you figure out the rest of it. Equal of and then the bonus third is just a combination. We're going to look at both of them together. The C is important. The first one that I wrote here, the last side of the looks like we're going to use the natural log of x as the basis for that. So let's go ahead and sketch the natural log of x. So this is right. So here's Well, now it says to take the vacuum channel out, which is in orange, and do the next one, which says no, I'm going to make it do. What do I make it do? 420.